See Lindelof videos, analyze a polynomial function. So here we're given this function, f of x is equal to the quantity x plus square root 3 squared times x minus 2 to the fourth power, and we're asked to answer these four questions. First, list each real zero and its multiplicity. So the first thing I'm going to do is I'm going to take this piece out right here. So this is what I'm looking at here. Looking at this piece right here. And that's a factor, so I can find a zero out of it, possibly. So I'll bring this down and say I have x plus square root 3 equals 0. Then I'm going to solve this and say x is equal to the opposite of the square root of 3. Keep in mind that's not the same as saying square root of negative 3. In this case, not in this case, in every case, PEMDAS says we do exponents first. Radicals are a form of exponents, so we would do 3 to the 1/2 power. I'm not asking you to get an answer for that. And then you'd multiply that by this negative 1. So while this is undefined, square root of negative 3 is undefined, opposite square root of 3 is defined. It makes sense. It's real. The next question we're asking, this part up here says, what's its multiplicity? The multiplicity is the exponential value. So it's a multiplicity of 2. I'm just going to put multiplicity 2 and come back to what that means in just a second. The next factor we have is x minus 2. So I'm going to set that equal to 0. So x minus 2 is equal to 0. X is equal to 2. And that has a multiplicity of 4, doesn't it? So here's its multiplicity here. So it has a multiplicity of 4. So there's a multiplicity of 4. So that answers this part right here. The second part says determine whether the graph crosses or touches the x-axis at these x-intercepts. All we have to do is analyze the multiplicity. And remember, if the multiplicity is even, if the multiplicity is an even number, the function touches the x-axis there but does not pass through it. If the multiplicity, this exponential value up here, is odd, it passes through that 0. Does that make sense? Really, really important. So we have to look at this and say, determine whether it crosses or touches. So in this case, it does what? We look at multiplicity of 2. It just touches, doesn't it? It touches x-axis but doesn't pass through it. That is to say, if this is the x-axis, if this is the x-axis right here at opposite square root 3, so let's pretend this is opposite square root 3. This thing, in this case, we know what it's going to do. It's going to actually come down here. It's going to touch this and go back up. But it doesn't go all the way through the x-axis. It just touches it there. And then we go to this. We're like, okay, when x is 2, when x is 2, does it, so x is 2 would be over here, wouldn't it? I'm going to slide this over. If x is 2, so x is 2 over here, isn't it? So maybe x is 2 here. So x is 2. I can't tell you where this thing tops out, Matt, but it does top out. It maxes out here somewhere. I know that because it comes back down because it has to touch 0 here. The only way it can touch 0 is to come back down, right? Intermediate value theorem. So it comes down here. It touches. Now the question is, when it touches right here, is it going to pass through and go to a number below 0? And this thing has a multiplicity of 4. 4 is an even number, therefore it just touches and bounces, in this case, back up. Is that all right? So also, in the case of this one, touches x-axis. That is to say, it does not go through. So he did this part. The next part is actually a little bit challenging if you overthink it, but the next part says, determine the max number of turning points. Well, look at this for a second. Without expanding this, hopefully you can see, if I did expand this piece right here, if I expanded x plus square root 3 squared, I'd get an x squared here, wouldn't I? And if I expanded this, I'd get an x to the 4th power, wouldn't I? And x to the 4th times x to the 6th is its power function. So this is x to the 6th is the power function. Can turn x to the n minus 1 times. That rule is always true. So how many times can this one change direction? Well, look, it's to the 6th power. 6 minus 1 is 5. So Not it does change direction that many times. It could change direction this many times. So can change direction 5 times. 5 times. Right? So also the last thing here says determine the end behavior. The end behavior is what happens way out here, right? So we're looking at, let this be the x-axis here, and let this be negative infinity and positive infinity. Well, we know our power function is x to the 6th power, isn't it? So if you know what the general shape of x to the 6th power is, it's semi-parabolic. It kind of comes down like this. It gets kind of flat looking here. So I'm not saying this is the perfect illustration, but to get in behavior, you just write these two questions. You write, as x approaches positive infinity, f of x, the height, approaches what? Well, as I move this way, look, as I keep moving to the right, I'm stuck on the function. As I keep moving to the right, I keep going up, don't I? So in this case, f of x approaches positive infinity, doesn't it? That's the first part. The second part is when I go to the left, so I write that out as x approaches negative infinity, f of x approaches what? Well, as I move to the left, look what this thing is doing. It keeps going up, doesn't it? I'm moving it looks like I'm just moving up, Brendan, but I'm not. I'm trying to move to the left, but I'm stuck on the function. And every time I move left, I'm forced to go up, aren't I? So, again, f of x approaches positive infinity. Are we good? So that's how I would answer those questions.